In this video, we're going to take a look at nuclear decay and radiation. So radiation is any penetrating rays or particles that are emitted by a radioactive source. Radioactivity is a process by which materials are given off these particles and rays due to having an unstable nucleus. This was first discovered by Antoine Henry Becquerel with Marie Curie and Pierre Curie, looking at uranium, and they noticed when they had photography film next to uranium that these particles, as they emitted, were causing the film to therefore be exposed to energy and get these white spots. But not every single isotope of an element is radioactive or a radioisotope, that it being one that has an unstable nucleus. So the first type of decay is called alpha decay or alpha radiation. And when an atom breaks down through an alpha decay, it gives off an alpha particle, which is a helium atom with no electrons attached to it. So here we see uranium-238 going through an alpha decay, breaking down into thorium-234, and giving off again that helium atom with no electrons, that helium, 2 protons, 2 neutrons, giving it a mass of 4. So these particles are pretty large, and they can be stopped by a piece of paper. So let's see how you could put together this process by yourself and come up with the radioactive equation for this alpha decay. So we're going to take a look at bismuth-187 and put it through an alpha decay and come up with an equation. So first we have to find bismuth-187. So again, 187 is the mass. Bismuth with an atomic number of 83. So bismuth-187, 83. And then again, note it's going to go through an alpha decay, so it's going to give off that 4-2 helium atom. And then from there, figure out what is left behind. So if I'm losing, again, the mass of 4, because I'm losing those 2 protons as we see down below, also 2 neutrons, I'm going to be left with a mass of 183, and the 2 protons from the 83 we started with leaves me with 81 protons. And then all we need to do is look up that 81 protons, and we see that it is thallium, and its symbol is TH. So the next type of decay is beta decay. And in beta decay, a neutron inside the nucleus breaks down, emitting off an electron and leaving us behind a proton inside the nucleus, overall keeping the mass the same of that given atom, but again, having an electron emitted away. So the most famous kind of example of this is in carbon-14, and how carbon-14, a neutron inside the nucleus breaks down, giving off again that electron. So the mass remains the same because electrons have no mass, but we're going to actually gain a proton because we have a neutron, again, breaking down and leaving behind this extra proton and losing a neutron. And these are much smaller than those alpha particles with the alpha decay, which we talked about, but still can be stopped by a block of wood. And the last type of decay is gamma radiation. And this gamma radiation that comes in association with both an alpha or a beta decay. If there's enough energy released, you get these gamma rays, which have, again, an awful lot of energy. There's no mass involved with them, but they're also really dangerous. So yeah, we see that here with our thorium breaking down into radium with an alpha decay and also some gamma radiation coming off. And that gamma radiation, again, is really strong. You need lead to be able to stop it. That's why, like when you go get an x-ray, they give you that lead vest to protect you from any type of rays with a lot of energy, like we see here. So all this radiation and decay isn't necessarily a bad thing. We use this in a good way to do carbon dating, to figure out how old a substance or a fossil is, because we can tell from carbon as it breaks down how much there is still remaining. So carbon has 3 natural occurring isotopes, 12, 13, and 14, but only 14 is a radioisotope and goes through beta decay, as we already saw. So every 5,730 years, half of the carbon-14 that was there has now decayed away and turned into that nitrogen. So based upon the ratio of the carbon-12 to the carbon-14, we can figure out how much carbon-14 has been lost, because there is a certain ratio that we expect to find it in, look at how much there actually is now, and again figure out how many of these half-lives it's gone through to figure out how old that particular fossil is. So when atoms split, we call that process fission. And when the nucleus again gets too large and too unstable, it can break up into smaller fragments. So we actually can make this happen on our own by bombarding these nuclei of different atoms with a bunch of neutrons to then build up the mass of that nucleus, causing it to become unstable. And then when that happens, it releases much more neutrons, which then bombard other atoms, creating this chain reaction. And as this happens, it gives off a lot of energy. that energy which we capture and use to create electricity. So here we see a power plant, a nuclear power plant, where we have this fission happening in our nuclear reactor over there on the left. And then as that energy is given off, we use that energy to heat up water, which creates steam. As steam flows, it turns this turbine, which then is connected to a generator, creating electricity, and then we cool the water down and then send it back in to be heated up again. And this process continues, again, turning that turbine over and over and over, creating more and more electricity. The opposite process, when we put things together, is called fusion. So fission is splitting apart, fusion is melding together. So when we combine the nuclei, that creates a nucleus of a greater mass, that is a fusion process. This process relates to even larger amounts of energy. However, the bad thing here is it's very difficult to control that process, and once it gets going, it is really difficult to slow it down. So we don't really use that for an energy source due to that difficultness and the danger that goes along with it. However, this is the process that fuels the sun. As hydrogen atoms fuse together, making larger helium atoms, it gives off a lot of energy.